I'd like to start the meeting today, and we have two great speakers. We have Praful from the UK, who stayed up late tonight, and we have Cod from Western Australia, and they'll be today talking about research, which is a follow-up to our CUI webinar that we had earlier this year, or rather about 6 weeks ago, when we had Peter Bock talking from the US on polysiloxane. For those of you who don't know, the Oil and Gas Technical Committee has a banner on the front of the ACA, and in there you can find a lot of papers on CUI, and you'll be able to find the presentations that we have today there at some time in the not too distant future. So to start today, I'd like to welcome you all, and I'd like to just make an acknowledgement to country. I'd like to respectfully acknowledge the traditional owners of the land on which we gather and pay respect to the Aboriginal and Torres Strait Islander community elders, past and present, who have resided in these areas and have been an integral part of the history of these regions. We also pay our respect to any Aboriginal and/or Torres Strait Island people present. My name's David Lake, and I am currently just an independent consultant. I've been a member of the ACA for many years, can't remember how many, and have been involved in the Oil and Gas Technical Committee since prior to the Darwin Conference, which is over 10 years ago. So the topic of today is CUI research and innovation. We have many events coming up in the not too distant future, and it would be good if you looked on the website and had a look on them. You probably get your emails from the ACA, which will keep you well informed of what's going on and what's happening. So Dr. Praful Sharma is the Chief Technical Officer of Corrosion Radar Limited in the UK. They're related to Saudi Aramco. Praful currently serves as the Chief Technical Officer and is bringing innovative corrosion monitoring technologies, useful industrial Internet of Things, IoT. Corrosion Radar invented a predictive CUI corrosion monitoring system, which is gaining global traction, addressing a big issue for the industry. Praful brings a vast industrial experience, especially in digitalization of corrosion management, on which there are several inventions to his credit. Prior to the current role, Praful worked for General Electric's R&D, where he developed several sensing NDT technologies. Praful obtained his PhD from Cranfield University in the UK. He has over 15 years of experience in industrial technology development, especially for asset integrity and automation of the oil and gas industry. He is also credited with over 15 international patents and innovations. And with that, Praful, I'd like to hand over to you for your talk. Now, all of you who would like to ask questions, please save them up and put them in the Q&A section at the bottom, and you can address them to all or to me, and I will ask the questions for you at the end of this presentation. So Praful, over to you.
Thank you. Just to verify, are you able to see my screen?
Yes, Praful, your screen is clear.
Wonderful. So thank you for the invitation. My name is Praful, and I'm joining from Cambridge in the UK today. That's where Corrosion Radar is based. And you can see my window. It's nighttime, it's midnight, temperature being 7 degrees Celsius. So you can understand why I am feeling slightly jealous of the good weather out there in Australia, sunny morning. Here I am, Corrosion Radar, and I'm also pleased to talk about our colleagues from APTS who are based in Australia and providing services, and we are having entry channel partnerships in Australia through APTS. So today the talk is going to be on online risk monitoring of CUI especially for cold insulation pressure vessels and pipelines. And I can be contacted on the email ID, which is mentioned on the screen, and this presentation will be made available. So to start with, let's start with some interesting cartoons, which we keep hearing about in the industry. Um, these are the regular conversations we hear in the industry. So here are two characters, Rob and Bob. Rob, I need you to cut the budget on CUI management by 20%. Boss, CUI is our biggest issue. We need to do more. So the key question to the audience is um, whether is CUI one of the damage mechanisms in your plant, including stress corrosion cracking, and we'll come to that in a minute. But you have the best prevention processes, coatings, insulations, RBI already. Yes, but still CUI is happening and we need to locate it effectively. So the question is, how are you managing CUI currently? Is the focus is on coatings or insulations, inspections, or risk-based inspections? Um, what is the methodology, and is that working? And then invariably people again find CUI, again there are leaks, and they need and the supervisors thinks we need to increase the budget, but how CUI prevention is not yet effective. Why? So how can CUI management be improved? When and where are risks to insulations, coatings, and CUI? And that's what the talk today is about, that we are still trying to understand it. And I'm sure colleagues from Curtin University, Cord, is going to talk more about in-depth research they are doing. So it's not a solved problem. It's still, we are trying to understand it. We need to manage it better. It's a systems issue. So what is this CUI? Corrosion under insulation. I'm sure there are a lot of experts out there uh, who know much more than me on this topic. But CUI is among the top asset integrity issues. Australia is no different in this aspect, but there are global issues. It's not only tropical climate in the Southeast Asia, it's not only South America, it's still in America as well, USA, Canada. We hear about this problem widespread in Europe and Middle East, whatnot. So CUI is among the top asset integrity issues in oil and gas and petrochemicals. And now we hear that it's also a big issue in other industries such as fertilizers and chemicals. And now due to energy transition, people are still forward thinking on that. Majority of the pipeline failures have been reported due to CUI in various shapes or forms. And in case of offshore platforms, especially when we talk about North Sea, uh, more than 10% of the overall maintenance budget goes to CUI. So you can see why this topic is so important. Now, the pictures on the top right are published pictures coming from one of the publications from Malaysia, where they really are showing the extent of it in that region. This is similar picture can happen anywhere in the globe. And I'm sure Australia also sees some similar effects. You can see CUI is actually on the outside surface of a pipe or any equipment, but it remains hidden due to its surrounding insulation. The conventional wisdom says that it happens in a particular spots, which can be the lowest points of water ingress, because CUI is corrosion, so it needs water. So water needs to ingress, and that's where it starts. But it can happen even unpredictable locations, not only on bands or lowest positions, but it can happen unpredictable locations. So how does this happen? So as far as CUI is concerned, it needs insulated assets, but this insulation becomes a devil if it allows the water to go in, and the water damages the coatings. And there's a lot of research going on in coatings on this topic. But coatings, if they get damaged, then corrosion can happen, and ultimately leaks can happen. So what do people do? They either do visual inspections. That's the best method right now. And also there are non-destructive testing methods, which are mainly spot techniques, pulsed eddy current, or X-rays. But again, it's not foolproof. Nothing is foolproof here. There's no silver bullet. Many times CUI can remain undetected, The problem is the issue is so large scale that the volume of the problem is just too huge. So there are chances that it can remain undetected. And it happens in certain temperature ranges. Now, this is a debatable topic. I'm sure our researchers probably know much better, but the conventional wisdom says that it happens pretty much anywhere between -4 degrees Celsius to up to 175 degrees Celsius. However, water evaporates above 100. However, the water can be looping inside um, as a steam and humidity inside the insulations. But there are intermittent operations as well. Sometimes, for example, in case of dryers or dehydrators in petrochemicals and gas processing, which goes from minus temperatures to plus temperatures because of the nature of the operation. And it's a very, very bad, severe issue of CUI there, because coatings, they don't like these oscillating temperatures. So that's on the CUI. Now there's another element here, is the predictive corrosion management. The world is moving towards predictive corrosion management rather than reactive. So, and it's being enabled by analytics, predictive analytics, and industrial IoT. And I'm going to talk about that today for CUI perspective. The context of that is the current practice of management of corrosion is mainly through human judgment and guess risk based methods, combined with periodic manual inspection and entity. Basically, it's reactive maintenance in the sense of the corrosion might have happened already, or it can lead to unscheduled shutdowns. So there's a safety risk. It's not a foolproof method, and it's very expensive. Now people have moved to preventive methods, and now the emerging practice is predictive methods, where even the online methods like sensors provide continuous monitoring, and it can be combined with knowledge bases and industrial guidelines to do automated risk profiling of the assets. Now, this risk profiling means condition-based assessments, and the inspection can happen after that in a more informed manner rather reactive manner. So this is predictive maintenance to minimize cost and increase the safety. And this is the new era which we are seeing. Now, how does this happen? So this is an example of what I represent is corrosion radar, but there are many other similar examples of monitoring through sensors. So in this case, this is a CUI monitoring system invented by Corrosion Radar. It's a spin out of Cranfield University in the UK, where the original research happened and development happened. So in this case, you see the sensors are shown in the orange colors. They are effectively covering a wide, long range coverage. And they are placed in various ways, helical or straight length, or even mesh or ring fashion, mainly to cover the assets and detect either moisture. So there is a moisture sensor, or in the same form factor as a corrosion sensor. And this gets connected to the electronics, and the electronics collect the data and transmit wirelessly to dashboards. Now, this is battery powered device and electrically powered device as well. There are various wireless protocols possible, but the unique benefits here are the long range and spatial coverage, flexibility, and decision management system with softwares. Now, you may ask, okay, so this looks like a heat tracing system. So yes, it is indeed a heat tracing system look alike. It gets installed very similar to that. It gets installed under the insulation. Normally, whenever there's a planned inspection already planned, turnaround is planned, that's the best time to install it. In case of new assets at the construction design stage, that's a good time to install it. For small pipe diameters, we recommend straight length for maximum coverage, and for larger pipe diameters, we recommend a helical sensor coverage. This covers wide temperature range, right from LNG temperatures of -190 all the way till up to 300 degrees Celsius for oscillating intermittent operations. So it's wide temperature coverage. At a time with one electronics, up to 100 meters of sensors can be covered. Let me see if I can minimize this. Anyway. So what is the principle of the electronics? The principle of measurement here. The core sensing principle is called electromagnetic guided radar, EMGR. Now this is a patented technique by Cranfield University and subsequently Corrosion radar. It is based on the wave reflection or time of flight, basically electromagnetic wave reflection of time of flight to locate moisture or corrosion on the sensor. So in this case, hypothetically, there's a pipe in black color, and at the top, the sensors are in close proximity to the pipe. And you can see there are two hotspots are getting developed, which are two risky locations are getting developed. It may be due to water ingress at these locations. So the moisture sensor, once the water touches the moisture sensor, the local impedance of the sensor changes. Now it need not touch the pipe. The sensor is detecting everything on itself. So it's a kind of proxy to the pipe. And the signal looks like a reflection, a peak signal coming from there. And based on the distance, it is located exactly where it is. That's where the inspection can happen. So it's a risk localization tool. Happy to say that this technique, EMGR, recently got an award in Corrosion 2021 conference for MPEAK Innovation of the Year award. So now what it enables, the era of risk-based assessments, especially dynamic risk assessments. So let me explain this a bit more. So this is about optimizing the inspections and increasing the safety. So what happens normally is left-hand side is the risk-based assessments or risk-based inspections. RBI is a standard practice in the industry, but it's very static. Once you do it, it doesn't change over time. However, the risks are changing over time and we don't capture it. So that's the problem. In this case, hypothetically, there are three assets, for example, asset 1, 2, 3, and they have a different risk profiles, consequence of failure and probability of failure to be low, medium, or very high. Now this in year 1 will look very similar to year 5 or year 10 unless it is updated manually, and it's a huge exercise if it needs to be updated. So this is not periodically updated, does not reflect field conditions, and so there's a scope of optimization. Now the new era using sensors and online monitoring can be that the moisture sensors converted to risk assessments, and then we have the ability that every year automatically the risks change from low to, say, in this case, if water comes in, it becomes high. In case of very high risk assets, it becomes low because no water is there, etc. So it's periodically updating manually or automated and incorporating the industry guidelines, API 581, and this can optimize the inspection cycles. For example, in case of asset number 2, which was high probability of failure originally, low probability of failure originally, so it would not have been inspected, but now it is high, so it needs to be inspected at some point because it's a safety issue. Similarly, for asset 1, which was very high, it becomes low, so which means the inspection of that is unnecessary because there is no evidence of water or risk there. Now, how does this happen? Is the probability of failure in this example, we are using RP 109 DNVGL guidelines. Similarly, API 581 is another guideline. Normally, the risk assessment says 5x5 matrix, probability of failure and consequence of failure. The consequence of failure does not change over time. It may be safety or financial. It depends on the type of asset, fluids. But the probability of failure can change over time because of, say, water ingress and change conditions. And that's what we make it variable rather than static using monitoring. So probability of failure. And that's what enables dynamic CUI risk assessments. Now, these are examples of risk localization. So I talked about dynamic risk, but this is now a second step. It is about localization of risk for optimized inspection scoping. Now, this example of integration of corrosion radar technology with CUI risk assessments based on API 581. There are two scenarios here which can help. Now, on the left-hand side is avoiding over inspection. There are two pipes here, it's a similar profile, but one of the pipe is shown in red color is very high in risk. Red means very high. So the conventional inspection scoping using RBI will very likely say that this needs to be 100% visual inspection. Visual inspection means you have to remove the insulation. It's expensive. But then if we combine it with, say, monitoring, say in this case, the sensors are installed and they are saying that, hey, yes, RBI is saying red, but the sensors are saying that these are green conditions. There's no water or humid condition inside, but there's a slight issue in somewhere in the middle. It's a medium type risk using API 581. Now, if we combine both the information, then we can optimize the inspection that, hey, we need not inspect it all of it. We just need to inspect probably that 1 meter. So that will avoid over inspection. Similarly, on the right hand side is a scenario where we want to avoid under inspection. So in this case, again, the same pipe. If it is green all throughout using RBI, there won't be any planned inspection. However, in reality, the water might have gone in and nobody will notice that. So that will be captured by the sensors. And then it will recommend that, hey, yes, it is indeed right that it's green, but no, there's a red condition developed locally. So go and inspect it at some inspection interval. So this needs to be inspected for safety reasons. So this is the next step of combining with RBI. How can we take condition-based data to effectively define the inspection scope? There are a few case studies I'll go through. So this is a case study generated by the NZTC. It used to be called OGTC in the UK, Oil and Gas Technology Center. It's a consortium of North Sea oil operators and the government to validate and promote technologies. Now we are this was funded by them, so they created this laboratory of CUI with heat tracing to increase the temperature, and then corrosion radar node. You can see the electronics there and the sensors being installed in a helical fashion on a rock, on a cellular glass insulation over the top, and at a particular location there was a salt solution being injected, and the pipe locally had the coating removed to simulate damaged coating here. So you can see over time the corrosion location, where the water was. You can really see the corrosion happen on the pipe, but also there is a corrosion on the sensor, because the corrosion sensor is a coupon. It's the longest coupon in the world. It self corrodes it, and then it detects where that coupon is getting corroded. Similarly, the white color is a moisture sensor. It detects where the water is touching the sensor. So the results of that is shown in this way here. There are 4 pillars normally of the whole process of the system of monitoring, where the electronics is the system and the hardware. It transmits the data for remote monitoring to detect and localize where the water is, and the corrosion sensor is detecting that. And then the next step is to pass it through risk analytics modules, which quantifies the risk with different industry guidelines. It may be in this case, it's DNV guidelines. So it's a CUI risk. Then the components of that is coating risk, insulation, water wetting risk, etc. And then the next step is to localize it, that, hey, it is at actually this location, which is 8 meters from the electronics, and it is increasing over time with a very high quantification probability of failure. And finally, it is localized to an actual pipe that, okay, this is the location where the risk is. If the inspection needs to be planned for the next 5 years, this is the location to watch out for rather than the whole pipe. So this is how the optimization is achieved. This is another case study. So Corrosion Radar is partially owned by Saudi Aramco. So this is a case study, published case study from there. This is a dynamic risk assessments of an LPG pipeline operating at minus 45 degrees Celsius in arid climate in Saudi Arabia. And you may ask, hey, at minus 45 degrees Celsius, there's no CUI, there's no corrosion, but this goes through a intermittent operation. Say this is this sometimes gets shut down because there's a I think this is a buffer unit, so it's sometimes shut down, so it goes to a atmospheric temperature. That's where the foam glass insulation can absorb moisture inside and trap the water and condense it on the asset. So this system was deployed there, and again the similar process of system monitoring, remote monitoring the water. So there was actually this was injected water by the end users uh, to do a validation and approve the technology. So in this case, periodically the water was injected at a particular location and it was detected rightly. And subsequently, the risk assessments detected that it's a very high condition, aggressive condition, and localized it to a particular pipe routed. The sensor was routed through a particular pipe for tests. So in this case, again, the inspection would have happened at that location. So this is another case study. Now this is a case study C. I would say this is among my favorite case studies because this is closer to the home. It's in Netherlands, and it's a production column. Now we are seeing a lot of interest in production columns or dryers and dehydrators. Now in this case, it's a 25 meters high production column. The sensors are this production column had a history of CUI, and the asset owner had to put a scaffolding every few years. I would say every 5 or 6 years to do the inspection of CUI. And I think this is a pressure vessel category which needs regulatory driven inspection periodically. But then they said, okay, we want to avoid that scaffolding, so we need to move towards condition-based monitoring. And that's where corrosion radar sensors were installed. You can see the orange colors on the top and orange color on the bottom, helical fashion. And then they connected to the electronics in the middle, the blue box, transmitting data on the cellular network. And you can see the pictures of the sensors which are wrapped around on the asset with the mineral wool insulation and transmitting data. Now the objective here, we have not detected anything on this asset so far, but the objective is if nothing is detected, they will skip an inspection cycle, save a cost. But if something is detected, it will be highly localized. So we will be able to say where the angle and the height of that corrosive conditions, and the inspection will be done through a rope access rather than scaffolding of a targeted location. Now this is a huge cost savings if it happens. It's been 3 years of this installation, but so far no corrosive conditions, so it's a good news for the asset owner. So I would like to summarize what I talked about. It's about predictive CUI monitoring. I would go one step further, that it's with moisture sensors and or corrosion sensors, either or. Now this is leading to data-driven RBI. We call it dynamic RBI, but RBI, rather than a static process, we're making it dynamic and more informed for optimization of the inspections. But also, if some people are not following RBI, it's fine. This is still early risk detection of leading to reduced unplanned shutdowns, predictive maintenance, and finally CUI prevention, because some of the asset owners, especially Norway, Europe, they're starting to say that it's better to prevent rather than inspect. Prevention is normally done through coatings or better insulations, but if we know that there's a wetness going on inside, then probably a prevention can be done by mitigating that wet condition, because so far the industry is struggling with water protection. Uh, there's only so much we can achieve with coatings and best practices of insulations. So this is more of an assurance additional monitoring tool, even for critical assets to achieve efficiencies. So I'm open to questions now. This is the end slide. And again, our our partners in Australia are APTS, Andre. You can contact them. It's the email ID. So David, over to you for questions.
Yes. On the sensors, how close do they have to be to the steel surface for this to be effective? Because the moisture could be just below an outside covering, but not penetrated some of the closed cell insulation. So where is it actually located?
So that's very good question. Normally, we would suggest that because we are monitoring the pipe surface, it should be close to the pipe surface. For the operation, that's not a necessary conditions, but it's an ideal condition if we can put it on the top of the surface. However, there is a galvanic disconnection between this asset and the sensor because there is a plastic sleeve between them. So the ideal location, even with foam glass insulation, which I'm showing here is an example of a foam glass insulation, is directly sensor on the asset surface and then a foam glass insulation. Because the foam glass insulation is a closed cell. So that's an ideal condition for installation.
So can it be installed further away and you still get meaningful results?
So the sensors function normally. They can even function outside. We test them on the table, on a normal table. So they function normally. However, the benefit here, the assumption here is they should represent the condition, corrosive condition or corrosivity of the pipe or the asset. So the closer we place them to the asset, the more realistic results they give. If we place them far away, say, then the conditions they detect will not be representative of the conditions seen by the pipe. So yeah, it's ideal to have it in proximity to the asset surface.
Okay, and we have a question here around the pipe supports and how we manage around those areas.
Yeah, so this is, as I said, this is like very similar installation to a heat tracing system. So even when a heat tracing system goes around pipe supports, or in this case, I'm showing a flange. So this goes around flange in the same way with an additional buffer length of the sensor. Again, same heat tracer also goes around it with an additional buffer length and goes around it. So I think every installation is designed on the site as to how the sensor layout is, with the pipe support being, it is installed in lieu of where the pipe support is and goes around it. Now, that's on the installation of the sensor. However, pipe support or any of the nozzles of the pipe or any of the flanges, they are an interesting case of complex geometries leading to CUI, because that's where water goes in, because that's a weak link. That's where moisture goes in the pipe supports. That's where insulation is slightly open and not perfect. So I think the sensor needs to be placed, routed through those locations to be realistic about covering, high risk locations. So yeah, I hope that answers the question of not only installation, but also routing it through those pipe supports and critical locations.
And one last question, what is the theory of this technique based on insulation layer conductivity change or pipe wall thickness difference, from one of our guests?
Yes, so the technique is neither of that. In fact, it does not interact with the pipe at all or the asset surface at all. It does not measure anything on the pipe or the asset surface. It does not measure the thickness reductions or corrosion on the surface. All it does is, it is, in case of moisture sensor, it is detecting moisture on itself. Say when the condensed water touches the moisture sensor, there's a signal comes that, hey, this is the location because of time of flight. It's basically a radar signal, the same radar signal which is used in spacecrafts or satellites. We pass the similar signals into the sensors and detect where the water is touching the moisture sensor. But it does not mean that the pipe is getting corroded. It just means that the pipe is getting subjected to a corrosive condition, and hence it is a higher risk. So this is a risk monitoring technique. Now, when it comes to corrosion sensor work and look very similar. For example, in this picture, you can see corrosion sensor on the right-hand side, within the blue cage, and the white one is the moisture sensor. So they both look like wires, but the corrosion sensor is self-corroding. The outermost layer of the corrosion sensor is made of carbon steel elements. They corrode, self-corrode, and it acts like a coupon. Now, the coupon corrosion does not mean the pipe is getting corroded. It just means that it is a high risk location. So in this case, you see this case study that this high risk condition actually led to pipe corrosion as well as no corrosion on the coating surface, and the sensors got corroded. So all it is measuring is corrosion on itself and indicating that this is a high risk location.
Okay, Praful, I'm afraid we've run out of time. Thank you very much for your presentation. There are a few more questions which I'm sure can be accommodated. You put your email address up at the beginning, and for those of you who don't know, it's very, very late in the UK, so Praful's probably going to leave us and go and get some sleep now. So thank you very much for your presentation, Praful. It's been interesting, and yeah, I'm sure a lot of people will consider it on their high-risk piping and vessels. So thank you very much.
Thank you for the opportunity, and feel free to contact us or Andre from APTS, and we will be happy to interact and talk more. Good. Thank you for the opportunity.
Pleasure. Our next presenter is Dr. Thanok Podchanabuton. Cod, we all know her and lovingly know her as, and we, Cod, you can correct my pronunciation.
Yeah, no problem. You're not the first person to, yeah, you're not the only person.
Okay.
Having trouble. Okay.
Just let me finish the introduction. Cod is a senior lecturer at Curtin Corrosion Center and corrosion education lead. She is currently working with industry partners on corrosion under insulation and has an interest in innovative strategies in controlling CUI. Cod also specializes in internal corrosion in the upstream oil and gas production, corrosion monitoring using electrochemical methods, both in field and in the laboratory, surface and chemical characterization methods. She has been a principal investigator for many industry funded research projects relating to failure analysis, corrosion and corrosion management, predominantly in the oil and gas industry. Cod is a leader in the oil and gas technical committee, which I'm part of and she's part of. And she's also one of the editors to get papers on CUI onto the website. So she or I are contactable to do that. Without too much more ado, over to you, Cod.
Okay, thank you, David. Just to make sure everyone sees the screen.
Yes, Cod, the screen's good. You've just got is that on full screen? Yes, it's just a square. That's all right. Good.
Yeah. So the title of my presentation today is Lab to Field, CUI recent research findings and the future direction. So just a little bit overview of the Curtin Corrosion Center. So we're located in Perth and we've been around 30 odd years now. And at the moment we have over 60 staff and students. And the topic below, the topics under the slide here shows the key topic and research themes we are working on. And you can see that CUI is one of them. And since 2014, 2015, we've been growing in terms of the number of projects related to CUI, coating under CUI. And at the moment, we have 6 people working on this topic. So we have Dr. Yang Ho focusing on the corrosion monitoring with the machine learning and the electrochemical noise method that she's focusing on. And we also branch out to, as coating is one of the key barrier to CUI, we branch out to study and degradation of coatings. So Ching, Janice, and Saleh are working on coatings and the degradation of coating under high temperature and under when coating is applied on different substrates such as carbon steel and stainless steel. These are the topic that these 3 are working on. And Nicholas is our new postdoc, and he's working on thermal insulation coating as another way to mitigate CUI. Just focus on today's presentation. This is the key takeaway that I would like to come to this conclusion at the end, is to highlight that the insulation materials will affect the risk profile of CUI, and the aging of the insulation material is critical to the changing of that risk profile. So when we introduce this insulation in the beginning, the fresh insulation is not necessarily the same as that insulation 2 years, 5 years from that installation. And therefore, critical properties such as water uptake, water retention, or leaching of corrosive chemicals from the insulation will change over time, and that will affect the risk profile. Also, when we look at the way to prevent CUI at this moment, protective coatings is one of the key components, and there are a few key considerations for qualification and the selection of the coatings that I would like to highlight in this presentation. So if we look at the cross-section of a pipe, we have pipe, we have coatings, and we have jacketing, we have insulation and the protective coating. And we know that the insulation materials can affect the CUI in different ways. The first one is that due to different properties in terms of the water retention, it can prolong the wet time. It can create the environment, enclosed environment where water can be trapped and corrosion can proceed undetected. It can also leach corrosive chemicals such as chloride, fluoride, or sulfate. It can also leach inhibitive chemicals, and these include silicate, for example, or some pH neutralizing compound that increase the pH of the water when enter the insulation. And these properties can be influenced from the high temperature exposure, which is not generally provided to the asset owners or provided to the end user, how that the thermal aging of that insulation would be. And the protective coating is also a key component in the insulated system. So first we look at the insulation materials. So at the moment, there are a few guidelines or acceptance criteria when we select the insulation materials. The first one being the ASTM C871 and C795. So these two ASTMs go together. So the one basically say how to leach or how to test the leachable ions of insulation material, and the other one provide a specification of that for use with the austenitic stainless steel. So we can see that in the domain diagram here, it provides like an envelope of where insulation is acceptable in terms of the leachable ion content, and that is a ratio between chloride and fluoride versus the sodium and silicate. So high concentration of sodium and silicate lead to a more inhibitive effect, so that would be within the acceptable range. On the contrary, if the insulation leach chloride ion to the unacceptable amount, then it would fall out of this envelope. Another guidelines that it has been used is the API 583. There's a figure in that standard that shows the ratio of the basically the diagram of the chloride content with the operating temperature and the compatibility with different material with respect to the risk of stress corrosion cracking. The EFC guidelines number 55 also suggested that the acceptable insulation material should have a halide ion content. In this case, it's both chloride and fluoride, less than 15 ppm, or a pH between 7 to 10.5. So these are the existing industry guidelines for asset owners or for the end user to rely on when it comes to the selection of the insulation material for different application. So we can see that it focuses on the chloride and the pH. So what we're trying to do here is to look at different types of insulation materials and to see whether or not it it changes in terms of the properties, chemical properties, and how it affects the susceptibility to pitting corrosion of 316 stainless steel. So we ran cyclic potentiodynamic polarization at 80 degrees with 316 stainless steel. So we tested the insulation as received and as it's thermally aged. So let's look at the first insulation, the insulation A. In this one, it was fibrous mineral wool insulation. So we can see that all of the insulation didn't change much in terms of the pH, but insulation A had a significant drop in the pH with the aging time. So if we take the information, just the fresh insulation at the aging time of 0, so all of the insulation would meet the criteria provided by the FC that the pH should be between 7 to 10, 10.5. But as you can see that the, particularly in the insulation A, the pH dropped significantly. After 8 weeks, the pH come down to about 6.5 and steady around that 6 to 6.5. So this suggested that during the thermal exposure of insulation A, there is some change in the chemical composition, either the degradation of the additive that leads to the leaching of the acidic chemicals. If we would just take information from the fresh insulation, we would miss this potential change in the properties of that insulation. Another test that we did was the leachable ion. So here we look at 6 insulation, but I'm presenting at 3 to show 3 different cases. So the first one being the insulation C, you can see that most of the insulation at different aging time didn't change much in terms of the chemical composition of the leaching liquid. So all of them still within the borderline range, still within the acceptable range. One of the insulation E, it did not change at all after 16 weeks of aging at 150, whereas one of the insulation F, and this one is, I think it's a rubber type insulation, and that did not meet the criteria from the beginning at all. It has a high chloride content. So with this risk of the chemical composition, we also ran the cyclic potentiodynamic test because the chloride content will affect the susceptibility of pitting corrosion. So in this case, we look at 4 different insulation materials from fresh insulation, and the leachates were spiked with 500 ppm chloride. The reason that we spike with some chloride is because first is to enhance the conductivity of the solution, and second, the past project that we obtained the insulation from the field, it shows that over time chloride will enter the system anyway, and therefore the introducing chloride content is not unrealistic. And what we can see here is that different types of insulation material can lead to a different risk in terms of the pitting susceptibility. So here, there are a few features on the cyclic potentiometric scan that we generally look at. The first one is called hysteresis. So insulation D is what we call a negative hysteresis, and that is the material is not susceptible to pitting corrosion because the reverse scan has a lower current compared to the forward scan, meaning that the passive region of the stainless steel was still intact even after polarizing anodically. When we have the positive hysteresis, and that is in the case of insulation A, E, and F, is when we see a significant increase in the current density at a certain potential, and that we call breakdown potential. For example, this is the breakdown potential of insulation F, and we use this value as one of the parameters to look at when we consider, when we try to rank the susceptibility to pitting corrosion. So here what we say, what we would conclude from this is that insulation F has a lower pitting potential compared to the insulation A and E. And there are a few other characteristics that we could obtain also from the graph. But the highlight from this slide is to show that different types of the insulation material will provide with different pitting susceptibility. So when we increase the thermal aging of the material, so here in the case of insulation D, when it was fresh insulation, there was no hysteresis found. So the breakdown potential was not obtained. But we repeat the same test with thermally aged insulation. And what we see is that we see a significant drop in the breakdown potential, showing that over time, after aging to a certain degree, the insulation can change and it provides different risk to the substrate. So this is a highlight of the insulation part of the presentation, to show that the high temperature exposure affect the pH of the solution. It affects the concentration and the types of leachable ions. It also affects the pitting susceptibility of stainless steel. And what we could look at, how we can use this study in the field, is that when we receive the product data sheet, for example, we have more questions to ask the vendors in terms of what is the risk of the thermal exposure? Is the insulation material thermally stable? And can we have other tests that is not currently used as a guidelines, as a screening tool to compare the potential risk corrosivity of those insulation materials? So on the coating side, which is a key barrier for CUI, at the moment, in the industry, there are two standards. One is NACE and one is API, and they both refer to these two tables, showing the selection of the coatings with different operating temperature. So for example, if the temperature is somewhere between 100, so there are few coatings that could potentially, coating class that could be used. But there's only one industry guidelines in terms of the qualification, and that is ISO 19277. And these guidelines provide a qualification methods for coating for use under insulation. So this diagram shows a summary of the test methodology provide in this standard. So first, they suggested that the coating should be artificially aged to simulate different conditions, such as when the coating is applied as module, and then it takes a while before the component get insulated. So that coating could be exposed to UV or salt spray for a period of time. So that is the step one, which is artificial aging. And then the CUI exposure, there are 4 types of tests provided that in that standard. So there are 3 tests that are not required to use insulation, and only the Houston pipe test, which is outlined under here, suggested that the coated sample would need to be insulated with whatever insulation to be used. We can see that the standard focus on the thermal cycling of the coating, because we know that temperature fluctuation of the coating is a way to accelerate the coating degradation. So what the standard basically simulate is the dry heat, water immersion, water evaporation, and the thermal cycling. It does not simulate the interaction or the compatibility of coating and the insulation material. Houston pipe test is only there in the standard as an optional test. It's not required. But there's a study done and presented at NACE a few years ago that shows that different insulation materials will affect the coating behavior and performance. One of the coating that was studied in that conference paper showed that it performed much better when it is insulated with calcium silicate and compared to when it is insulated with mineral wool insulation. So that is something to take into account when look at the qualification of the coating. Also, when we look at the way for coating to be assessed after the exposure, there are different ways to look at it. So we look at from the corrosion protection point of view, we look at the visual appearance, chemical properties of the coating, and so on. But the only visual appearance and degree of blistering, degree of rusting, cracking, and so on, and the adhesion strength value are commonly used. The other assessment methods are not usually provided or presented when it comes to the coating qualification. And what I would like to share here is we did the Houston pipe test on one of the epoxy coating under insulation. And this is a snippet from the paper that will be presented in next year. It's supposed to be this year, but it will be in February next year at the ACA conference. But what that study will show in more detail is the test methodology and how the different results, how the result is contradicting from the different assessment method. For example, here we can see that here is on the x-axis, we have exposure temperature, and on the y-axis, we have the adhesion strength. So when the coating exposed to at the lower end of the temperature, 60 to 80 degrees, the adhesion strength was quite high, even after 6 cycles of the Houston pipe test, so wet and dry cycle. The adhesion strength is still over 20 MPa. And that is similar to the baseline, which is highlighted in the dash line here. So it didn't change with time. At higher temperature, end of the test pipe, at 180 degree, adhesion strength is still very high, it's still 20 MPa. Even though the failure mode changed from glue failure to cohesive failure, the adhesion strength is still very high. So usually we will look at the adhesion strength and we could correlate that with the coating was not affected. But we took also the sample and we ran EIS on that particular temperature. So the sample is a vertical pipe. So we have a smaller PVC cup basically to attach onto the pipe, creating the reservoir of the electrolyte where we do the EIS. And this is on the right-hand side, show the difference in the EIS ran on the pipe section at 80 degree and 180 degree. So we can see a significant difference in terms of the coating behavior from the EIS data. So the test is still ongoing in terms of the project. So we're still looking at different types of assessment techniques. But what it shows is that the selection of the coating qualification test is important. It should be simulating the CUI conditions expected in service. So if it is going to be used with insulation and with different type of insulation, that coating should be studied in conjunction with that type of insulation materials, and to look at a more appropriate way and more comprehensive way of coating assessment techniques to obtain a different parameters, different properties of the coating, to be able to understand the coating behavior, performance, and the degradation mechanism of that coating. Just to a slide to show what we are doing as part of the Curtin-Curie Alliance is that we're looking at the different effect of substrates, so carbon steel and stainless steel. We are trying to develop a systematic test protocol for evaluating coating, particularly at higher temperature, to look at mechanical properties of the coating, to look at the to correlate with the degradation mechanism of the coatings from the mechanical point of view. We're trying to also develop test apparatus from the lab scale to outdoor field-like exposure. So here is the outdoor exposure. There will be 4 pipes and fitted with the overhead sprinkler to simulate wet dry cycle in a more realistic way. And moving forward, we are working towards the CUI risk prediction tool from the mechanistic point of view. At the moment, we are trying to secure a few more industry partners, and the project will kick off in Q1 next year. just a little bit of explanation of what I mean by mechanistic approach in terms of the CUI prediction is to break it down in terms of the CUI processes. We have the water ingress, we have water transport, and we have the corrosion process. All of these sub-processes have a sound fundamental knowledge behind it. So therefore, we plan to look at these step by step and look at how to predict the water accumulation, water transport through insulation materials, similar to what they do in the residential or in the building industry. And then we use the existing knowledge on the electrochemistry of the corrosion to identify the rate and the risk of localized corrosion of the CUI. And just a few acknowledgements to our current sponsors, Curie, Woodside, and Chevron. Yep, and welcome for any questions.
That was excellent, Cod, and your timekeeping is almost superlative. A quick
8:01, yeah, 7:01, 1 minute over.
One quick question for you on the insulation breakdown. I've never seen any of the suppliers of insulation give high temperature breakdown degradation properties of their insulation. How easy is that to find, or does it have to be done through your research?
I think it's not a difficult test. It's basically the test that they should already be doing for the fresh insulation, and they just have to repeat it with thermally aged insulation. In my opinion, they should provide that in the data sheet. But we can do it if you are interested for a third party or independent lab to do it.
Do I have any other questions from anyone? It looks as though people are just thanking you for your presentation. Cod, on the paint side and the corrosion failure through insulation, breakdown of the insulation, you still need the moisture to get in there, don't you? So this is a second level of risk rather than a prime risk.
Yes, we still need the water. Coating degradation is also accelerated in the presence of water, and once the coating breaks down, then the corrosion takes place. Yeah, so we need the water for that to occur. And the Houston pipe test basically introduce water every day for the next 6 weeks, and simulating that more number of wet dry cycles.
Okay, thank you. There doesn't seem to be any more questions, Cod, so that's no reflection on the presentation. I found it enthralling. It was excellent, and a topic I'd never really considered, the breakdown of the insulation to cause a higher risk for corrosion under insulation. So thank you very much for your presentation.
No problem. Thanks very much.
And everyone, don't forget, in the conclusion today, we've got our corrosion technicians webinar on November the 10th, featuring Nicholas Raphael from Mondo on nickel cadmium battery testing and refurbishment for pipeline protection, and the online seminar Expanding the Service Life of Concrete Structures, featuring 6 guest speakers. And lastly, but not least, our our Oil and Gas Technical Committee, which both Cod and I are members of, have an event, Failure Analysis of Microbiological Influence Corrosion, Global Experience in the Oil and Gas Industry. And I notice a couple of participants in that are in the audience today, especially Margarita. So thank you all. And with not too much further ado, have you got a final comment, Cod? But thank you.
Okay, thank you very much.
Bye.